Welcome to the deep dive. Today we're digging into how large language models might handle much longer sequences of text more efficiently. We'll be focusing specifically on something called sparse attention.
That's right. We're looking at the research paper, The Sparse Frontier. Sparse attention trade-offs in Transformer LLMs. Our goal is to get you, the listener, up to speed on the main ideas how sparse attention works, the potential benefits for efficiency, and importantly, the trade-offs involved.
Okay, so let's start with the basic problem. Why is standard attention in these models such a hurdle when you feed them really long texts?
Well, the standard self-attention mechanism, it runs into a scaling issue. During the initial processing, what's often called prefilling, the computation needed grows quadratically with the length of the sequence.
Quadratically, so double the length, 4 times the work, something like that.
Pretty much, yeah. You're comparing every part of the sequence to every other part. Then, when the model starts generating text, the decoding phase, it needs to keep track of the context. This is the KV cache, and that cache grows linearly with the sequence length.
Okay, so you've got compute exploding during input and memory use growing steadily during output. Both sound like serious bottlenecks.
They really are. It limits how much information these models can realistically handle at once.
Which brings us to sparse attention. How does that try to, well, fix this?
The core idea of sparse attention is approximation. Instead of calculating all possible interactions between queries and keys, which is what dense attention does, it calculates only a carefully chosen subset.
A subset, so it's skipping some calculations.
Exactly. The hope is that by skipping the less important calculations, you drastically reduce the computational load and the memory footprint, but without losing too much of the model's ability to understand the context.
Makes sense. The paper apparently breaks down these sparse methods along 4 main lines. What are those distinctions?
Right, 4 key axes. First is the unit of sparsification. This is about what you're making sparse. Are you focusing on individual tokens or maybe blocks of tokens or perhaps specific patterns like vertical stripes in the attention matrix?
Okay, the what? What's next?
Second is importance estimation. How does the model decide which units, which interactions are important enough to keep? This can be based on fixed patterns like attending to nearby tokens, or it can be context aware, adapting based on the actual input.
So how it chooses what to keep. Got it.
Third is budget allocation. You have a limited computational budget for attention now. How do you spread that budget across the different layers of the transformer model? Uniformly, or do some layers get more budget than others?
Right, distributing the savings. And the last one?
Finally, there's KV cache management. This relates mostly to the decoding phase. Since the cache can still grow, how do you manage it with sparsity? Do you still keep everything generated, or do you start evicting older parts of the cache?
Okay. Units, importance, budget, cache management. Lots of different ways to implement sparsity. The paper uses something called isoFLOPS analysis to compare them. What's that about?
isoFLOPS analysis is basically a way to compare apples to apples, computationally speaking. You fix the total amount of computation, the FLOPS, or floating point operations per second, and then see how different configurations perform within that same budget.
So it levels the playing field in terms of raw compute cost. What did this analysis show about, say, model size versus sparsity?
Well, for shorter sequences, they used around 32,000 tokens in the study. They found something interesting. It was actually more efficient to use a smaller model but make its attention denser, less sparse, than it was to use a larger model with high sparsity.
Huh. So for moderately long sequences, just throwing sparsity at a bigger model isn't automatically better.
Not necessarily within that fixed compute budget, but, and this is key, that finding flipped for very long sequences, like 128,000 tokens.
Oh, okay. What happened there?
At that much longer scale, the larger models using high levels of sparsity became more computationally efficient than the smaller, dense models operating under the same FLOPS budget. There's a crossover point.
That's a crucial finding. The benefit really kicks in at scale. Do they see differences between the input processing and the output generation phases?
Yes, they did. They noted that the decoding phase, when the model is generating text based on a long context, seemed to be more resilient to higher levels of sparsity compared to the initial pre-filling stage.
Interesting. So you might be able to be more aggressive with sparsity during generation.
Right.
The researchers also looked at just how sparse you could make attention before performance really tanked, right?
They statistically tested the limits. They tried to find the maximum sparsity level you could apply while keeping performance roughly on par with the standard dense model.
And what was the general trend?
Generally, they confirmed that higher sparsity was more tolerable during decoding, as we just mentioned, and also larger models generally seemed better able to handle higher levels of sparsity without performance degradation compared to smaller models.
But was there a magic number,
Yeah.
a sparsity level that just worked?
That's the catch. A really important finding was that even using what seemed like moderate sparsity levels often led to a significant performance drop on at least one task, even if it looked okay overall.
Oh, okay. So it's not a free lunch. Sparsity can hurt performance, and it depends on what you're asking the model to do,
Precisely. It underlines that sparse attention isn't some universal fix you can just switch on. It requires careful tuning and consideration of the task.
which leads nicely into another point. The paper stresses that no single sparse attention method was the best across the board. Why such variability?
It really came down to the specific demands of the task, and again, whether it was the prefilling or decoding stage, things like the best unit of sparsification blocks versus tokens, for instance, or whether using an adaptive budget helped, well, it depended heavily on the task.
Can you give an example? How did tasks influence which methods shown?
Sure. Take tasks focused on retrieving specific bits of information. The paper calls them low-scope, low-dispersion tasks. Here, performance drops often correlated with how many separate pieces of info you were looking for. Token-level methods saw performance dip somewhat linearly as you compressed more in a story retrieval task.
Okay. What about other methods or tasks?
Well, block sparse, a chunk-level method, actually struggled during pre-filling for multi-query retrieval. But then another method called quest, which is page-based, did quite well during decoding for similar retrieval.
So different methods excel at different stages, even for similar tasks. What about tasks needing a broader view?
For tasks needing more global understanding, like maybe summarization or reasoning across different parts of the text, high scope or high dispersion tasks, the chunk level methods like block sparse and quest tended to perform relatively better.
And what about adapting the budget? Did that consistently help?
The results there were also mixed. Some adaptive strategies showed benefits in certain scenarios, like one called flex prefill versus a non-adaptive method during prefilling, but another comparison during decoding showed less clear advantage for the adaptive approach. It wasn't a universal win.
It really sounds like a complex optimization problem.
Yeah.
The paper also mentions developing scaling laws, specifically for sparse attention. What are those?
Scaling laws in LLMs usually describe how model performance changes as you scale up things like model size or dataset size. Here, the researchers aim to do something similar, but adding sparsity into the mix.
So predicting performance based on size, sequence length, and how sparse the attention is.
Exactly. They developed a statistical model, log linear, specifically that tried to predict performance considering model size, sequence length, and the compression ratio achieved by the sparse method.
And did it work? Could they predict performance reliably?
They reported high R-squared values, which suggests the model fit the observed data quite well. It means these factors, size, length, sparsity, have fairly predictable relationships with performance, at least within the range they studied.
Does that mean we can confidently predict how a much larger sparse model would perform on even longer sequences?
The scaling laws generally did a decent job predicting performance on held-out data, meaning different model sizes or sequence lengths they hadn't explicitly trained the law on. However, there were some task-specific wrinkles.
Oh, like what?
For example, they noted challenges in accurately predicting performance on a multi-hop reasoning task, especially when varying the compression ratio and sequence length during the pre-filling stage. So while the laws provide a good general guide, task specifics can still cause deviations.
Okay, so wrapping this up, if you had to summarize the key takeaways from this deep dive into sparse attention.
I'd say sparse attention is definitely a promising direction for making LLMs handle much longer sequences more efficiently. The efficiency gains look particularly strong for very long contexts combined with larger models.
But there's always a but.
But yes, it's not straightforward. There's no single best method. The optimal approach is highly task-dependent, and you always face potential trade-offs where performance might drop on certain tasks, even if the overall sparsity level seems manageable. Careful evaluation is critical.
Right. And the really striking insight for me was that crossover point, where for truly massive sequences, a large sparse model actually becomes more computationally efficient than a smaller dense one.
That's a key point. It suggests where the biggest potential impact of these techniques might lie, enabling models to process amounts of information that are currently impractical with standard dense attention.
So a final thought for you, our listener. to ponder. Given that the best sparse attention strategy seems so dependent on the task and even the phase of processing, how might future systems dynamically adapt their attention? Could a model perhaps learn to switch between dense, block-sparse, or token-sparse attention on the fly, based on the input it receives and the task it needs to perform? That adaptability seems like a really interesting frontier.